In section 3.9, we continue on with our calculatory portion of this chapter with mass percent, which is actually a pretty straightforward concept once we've mastered the idea of molecular mass and molar mass. Now, the mass percent of something, just like any percent, it's the mass of whatever part you are interested in divided by the mass of the total of the object that that part is part of, and then put it in terms of percentage. So what does that mean as in English and in reality? Well, if we're looking at the mass percent of chlorine, so this guy, in CCl2F2, this is a chlorofluorocarbon, we can just simply look at the molecular mass of chlorine, so 35.453. We have to account for the fact that there are two of them. And then that will be the mass of element X in 1 mole of the compound. That's the top part. So 35.453 times 2 gives us 70.906 grams per mole. And now what's the entire compound? So to that, we have to add the 12.01 grams of carbon per mole. That's 1 carbon. And the 18.998 grams per mole of fluorine times the 2 fluorines. Okay, so that first one's pretty easy. 12.01 grams per mole and 18.998 times 2 gives us 37.996 grams per mole. So that means 70.906 plus 12.01 plus 37.996. The total for the whole compound would be 120.912. And we'd probably truncate at that second decimal because of carbon. Which I guess we could have taken more digits for, but whatever. Here we go. Grams per mole for the whole thing. CCl2F2. So that's the bottom here. That's this mass of 1 mole of the entire compound. So what we have then is the 70.906 grams chlorine over 120.912 grams of CCl2F2. We're not rounding yet because we're not to our final answer. Times 100% will be 0.906 divided by 120.912 times 100 to get it into percentage, and we're looking at 58.64% chlorine. And we're rounding to 4 sig figs because this bottom number, the way we calculate it, didn't really have a tenth, hundredth, thousandth place for the grams. So what does that mean at 58.64%? Well, we can use this as a conversion factor because this also means that we have 58.64 grams of chlorine for every 100 grams of this CCl2F2 compound. And we can use that either way. We can flip that over just like feet to yards and yards to feet. So we can ask questions like, how much chlorine is in a kilogram of CCl2F2? Well, let's see. So 1 kilogram of Cl times 8,000 grams for every 1 kilogram. So now we're in units of grams of chlorine. And we can say there are 100, start over, 1 kilogram of CCl2F2. My apologies. Okay, so times 8,000 grams for every 1 kilogram, and now we have units of grams of the whole thing. That's good, of the CCl2F2. And then we can multiply that by 58.64 grams of chlorine for every 100.0 grams of CCl2F2. And we get divided by that 586.4 grams of chlorine. Okay, so that makes sense because it's a little more than half chlorine, and half of 1,000 grams would be about 586. So there we go. Now, instead of mass, we can also go about this process using mole ratios, which is actually a little simpler if what we're really interested in is number of molecules or atoms in the first place. So we can use the ratios of the subscripts in a molecule as ratios all on their own. So for instance, there's 2 moles of chlorine for every 1 mole of this whole thing, which we can express as 2/1 or 1/2, depending on which way the conversion has to go. So if we have 38.5 moles of CCl2F2, then how many moles of chlorine are there? You can simply say there's 2 moles of chlorine for every 1 mole of CCl2F2. So that gets us 38.5 times 2. I should probably be able to do that in my head, but I can't. 77.0 moles of chlorine. And that 2 comes very specifically just from the 2 subscript. Alright, well, what if we want the mass of chlorine? So let's take a look at this. We have 25.0 grams of CCl2F2. How many grams of chlorine does that represent? Well, we can use that mass ratio that we had before, but that is only one way to do it. The way that you'll typically encounter this is you'll convert the grams of CCl2F2, which we said earlier was 120.91 grams per mole. .91 grams. CCl2F2. This is CCl2F2. Gotta give all the labels to this. 1 mole of CCl2F2. Now we can also use the ratio that there are 2 moles of Cl for every 1 mole of CCl2F2. And then finally say that there are 35.453 grams of Cl for every 1 mole of chlorine. So altogether that will equal C25 times 1 divided by 120.91 times 2 times 35.453, and as long as I punched everything in correctly, 14.7 grams of chlorine in this 25-gram sample. Excellent. All right, well, let's look at something even more interesting. And keep in mind, all this is just conversions. That's it. That's the entire process here. It's just converting from one thing to another. We just have to know what things are conversions and what aren't. So let's say we get this highly exciting set of questions here that the water has a density of 1.0 gram per milliliter. Okay, so that's a ratio. That means that will be a conversion somewhere in our problem, most likely. How many grams? Okay, so that's our answer we're looking for. Grams of hydrogen atoms, specifically, and are in 1 gallon of H2O. All right. So our plan is find out where to start. For where to start, look for the data. The data is going to be what is not a ratio about 99% of the time. So if you're not sure where to start calculating at, look for things that are not ratios, and that's likely where you start. So 1 gallon of water is our starting point. Our process here is going to be find the conversions that I need to get from gallons of water all the way to grams of hydrogen atoms. Okay, so what conversions do I know? Well, gallons and grams are in the different unit system, so I'm going to need some sort of conversion from gallons into something metric. Okay, so the easiest one I can think of here is the liters, 3.79 liters for every 1 gallon. Okay, so now we're in liters of water. I can see here that if I knew the milliliters of water, I could come up with the grams of water. So I'll go from liters to milliliters. Just trying to work my way over here. Grams of water seems closer to grams of hydrogen atoms, so I'm going to see if I can get to there. So to do that, I need milliliters. 1,000 milliliters for every liter. And now I can use this density to say 1 gram of water for every 1 milliliter of water. Excellent. So I figured out how many grams of water I have. That's where I'm at right now. Well, I can get here by a number of pathways now. I can go back to the percent hydrogen in water and work out that. Or I can work out the molecular weight of water and go to moles of water and then moles of hydrogen in water. And I think that's actually the way I'm going to go. So I'm going to go here to moles of water to go to moles of hydrogen, just H2, just moles of hydrogen, and then from there go back up to grams of hydrogen. Okay, so let's try that. Well, if we go to the periodic table, we got 1.01 grams for each hydrogen and about 16 grams for each oxygen. So multiply this times 2, we get 1 mole of water is 18.02 grams of water. Excellent. So now we have moles of water. So to get to hydrogen, we just say 2 moles of hydrogen for every 1 water. And that's from the 2 in the chemical formula. And now as our last step, erase a little bit of this arrow here. And we say, from the periodic table, 1.01 grams of hydrogen for every mole of hydrogen. All right, so this is set. So we can go from gallons all the way through all of these units, eventually, to grams of hydrogen. So here's my warning. What people really like to do, and this is a very human characteristic, is find out and memorize an algorithmic, meaning just a step-by-step process. What steps do I need in order to go from the start of a problem to the end of a problem? Well, the problem with that is you would have to memorize millions of different possible configurations in order to have all the possible ways that you can do something to get from one set of units to another. So just like if I had given you a problem where I said how many nanometers are there in a football field, you'd have to go to yards and then to feet and then to inches and the centimeters and the meters and down to nanometers again. You'd have to come up with a set of connections between what you have and where you want to get. For these types of problems and the problems we're going to be doing soon that are similar, you're going to need to just work out a series of connected ratios that get you from where you start to where you want to go. And there's no way to just memorize all the possible ways to ask a question and how to get to an answer. So 1.00 times 3.79. Okay, so gallons of water cancels with gallons. Now we have liters of water times 1,000. Now liters cancel, and milliliters of water are left, times 1 gram of water for every milliliter. So now we have grams of water. Divide by 18.02. And now we have moles of water. Now notice at this point, if you're kind of calculating along, that's 210.32 moles of water. That's a lot, right? But water is a very small molecule, very light, and a gallon is a lot of it. Okay, it's not a handful of water, it's an entire gallon. So this is a perfectly reasonable thing to have at this point. All right, so now we're going to take those moles of water, cancel out, and get moles of hydrogen. That's about 421. And now we're going to cancel moles of hydrogen out to get 2 grams. And we get 424. How many sig figs do we have? We have 3. So 425, this rounds to, grams of hydrogen atoms.